So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
In the beginning, there was an infinitely dense tiny ball of matter. Then everything went bang, resulting in the atoms, molecules, stars, and galaxies we see today. Or at least that's what physicists have been telling us for decades. However, recent theoretical physics research has introduced a new perspective, suggesting that the early universe may not be as early as previously thought. Instead, it could be part of a cyclical process where the universe undergoes a series of bang-bounce cycles that have occurred at least once and possibly in an infinite loop. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding to the intrigue, the James Webb Telescope has made a remarkable discovery that contradicts the notion that the Big Bang marked the beginning of the universe. This revelation prompts the question, if the Big Bang wasn't the beginning of the cosmos, then what was it? Let's find out. Scientists have a very good idea of the very early universe that we know and love as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser a long time ago than it is today. In that early inferno 13.8 billion years ago, all the elements that make us what we are were formed in the span of about a dozen minutes. According to this theory, our entire universe, all the stars, galaxies, and everything, was once the size of a peach and had a temperature of over a quadrillion degrees. Surprisingly, this fantastical story is consistent with all current observations. Astronomers have studied everything from leftover electromagnetic radiation from the early universe to the abundance of the lightest elements, and discovered that it all fits with what the Big Bang predicts. As far as we can tell, this is an accurate depiction of our early universe. But as good as it is, we know that the Big Bang picture is not complete. There's a puzzle piece missing. And that piece is the earliest moments of the universe itself. That's a pretty big piece. The challenge we face in understanding the universe lies in the limitations of the physics theories we currently employ. Combining general relativity and high-energy particle physics provides us with a framework, but as we delve deeper into the cosmos's initial moments, the complexity of the mathematics intensifies until it reaches a point where our current methods fail to provide meaningful solutions. One of the indications that there is unexplored territory is the presence of a singularity, an infinite dense point at the start of the Big Bang. Taken literally, this suggests that the universe was once compressed into an infinitely small and dense state, which is clearly nonsensical. Rather than accepting this at face value, it tells us that we require new physics to overcome this challenge. Our current toolkit just isn't good enough. To save the day, we'll need some new physics, something that can handle gravity and the other forces simultaneously at ultra-high energies. And that is precisely what string theory claims to be, a physics model capable of handling gravity and other forces in combination at ultra-high energies, which means that string theory claims it can explain the earliest moments of the universe. Within string theory, the concept of an ekpyrotic universe emerges, drawing its name from the Greek word for conflagration or fire. According to this idea, the Big Bang we are familiar with was sparked by a preceding event, indicating that it was not the absolute beginning, but rather a part of a larger process. Extending the ekpyrotic concept has led to a theory, again motivated by string theory, called cyclic cosmology. While the idea of a repeating universe has been contemplated for thousands of years, string theory provides it with a solid mathematical foundation. The cyclic universe operates as one would imagine, oscillating between big bangs and big crunches in an endless cycle, extending infinitely into the past and future. This theory of cyclic cosmology was put forth by renowned physicist Roger Penrose, who was awarded the Nobel Prize in 2020. Penrose was fascinated by a remarkable mathematical relationship between the early universe, characterized by extreme heat density and smallness during the Big Bang, and the projected future state of the universe, which is expected to be extremely cold, expanded, and devoid of matter. His groundbreaking theory suggests that these two states become mathematically identical when pushed to their limits. While it may seem paradoxical, the absence of matter entirely could be the driving force behind the creation of all the matter we observe in the universe. According to this perspective, the Big Bang originates from a nearly imperceptible remnant left after all the matter in the universe has been consumed by black holes, which eventually evaporate into lost photons within a vast emptiness. Thus, the entire universe emerges from something that, from a different standpoint, is essentially as close to nothingness as one can imagine. However, this nothingness is still a form of something. It constitutes a physical universe, albeit an empty one. The mystery lies in how this same state can be interpreted as both a cold, empty universe and a hot, dense universe, depending on the viewpoint. The key lies in a complex mathematical technique called conformal rescaling, which is a geometric transformation that alters the size of an object while preserving its shape. Penrose demonstrated that the cold, empty state and the hot, dense state can be connected through such rescaling, aligning their space-time structures, although their sizes differ. It is admittedly challenging to comprehend how two objects can be identical in this manner despite having different sizes. However, Penrose argues that the concept of size loses its relevance in these extreme physical conditions. In conformal cyclic cosmology, the sequence of events unfolds from an old and cold state to a young and hot state. The presence of the hot dense state is a result of the cold empty state, but this causal relationship does not follow the usual pattern of cause preceding effect in terms of time. In these extreme states, both size and time lose their conventional meanings. The cold empty state and the hot dense state exist in separate timelines. From the perspective of an observer within its own temporal framework, the cold empty state would continue indefinitely. However, the hot dense state it gives rise to occupies a completely new timeline of its own. It can be useful to think of the hot dense state as arising from, being grounded in, or realized by the cold empty state in a non-causal manner. These concepts have metaphysical implications and have been extensively explored by philosophers of science, particularly in the context of quantum gravity, where traditional notions of cause and effect seem to break down. When we reach the limits of our understanding, the realm of physics and philosophy intertwine and become challenging to separate. Conformal cyclic cosmology provides speculative yet detailed explanations for the origin of our Big Bang. However, even if Penrose's ideas find support in future advancements in cosmology, they may not address a deeper philosophical question regarding the origin of physical reality itself. How did the entire system of cycles come into existence? This leads us to contemplate the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. However, for the purpose of our discussion, we will focus on explanations within the realm of physics. There are three main possibilities to consider when exploring the origins of these cycles. Firstly, it's possible that there may be no physical explanation at all. Secondly, there could be an infinite series of cycles that repeat, with each cycle representing a distinct universe. The initial quantum state of each universe would be determined by some aspect of the universe that came before it. Lastly, there is the option of a single cycle and a repeating universe, where the beginning of the cycle is explained by a feature of its own end. The latter two possibilities are attractive because they avoid the need for uncaused events and provide a comprehensive explanation within the realm of physics. Penrose puts forth the idea of a sequence of endless new cycles influenced by his interpretation of quantum theory. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events, resulting in variations between cycles. This concept holds promising implications for experimental physicists, as it opens the possibility of detecting subtle traces or anomalies in the radiation left over from the Big Bang, which has been observed by the Planck satellite. Penrose and his colleagues believe they may have already identified these traces, attributing certain patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, other physicists have raised challenges to these findings, and the validity of their observations remains uncertain. The recent revelations brought forth by the James Webb Telescope have caused significant disruptions in the field of cosmology, as they defy our current comprehension of the universe and potentially undermine the validity of the Big Bang Theory. Astronomers have identified 6 colossal ancient galaxies that have earned the moniker universe breakers due to their immense size and age. These galaxies existed during a time when the universe was merely 3% of its present age, which is much earlier than anticipated for galaxies of such magnitude. According to established theories, the early universe should have been populated by small, youthful galaxies during this era. However, the newfound galaxies possess maturity and massiveness akin to our own Milky Way, presenting a perplexing enigma for scientists. The existence of such colossal galaxies in such close proximity to the Big Bang challenges the prevailing understanding of early galaxy formation. According to existing models, following a period of rapid expansion, the universe cooled down, permitting gas to coalesce and collapse, resulting in the birth of stars and galaxies during the Dark Ages. Nevertheless, the discovery of these massive galaxies suggests that the Dark Ages might not have been as devoid of activity as previously believed. Dr. Emma Chapman, an astrophysicist at the University of Nottingham, commented that these findings imply that the universe experienced abundant star formation much earlier than anticipated. Further observations and in-depth analysis will be essential to corroborate these discoveries and ascertain their implications for established cosmological frameworks. The research team intends to acquire spectrum images which will offer more precise distance measurements and enable better estimations of the galaxy's masses. Spectrum analysis will play a pivotal role in validating the existence of these objects and shedding further light on their nature. The unexpected nature of these findings emphasizes the ever-evolving landscape of scientific knowledge and the necessity to revise theories when confronted with new evidence. While it is premature to definitively dismiss the Big Bang Theory, the revelation of these massive ancient galaxies challenges our current cosmological framework and calls for a reassessment of our understanding of the early universe.